Welcome in. So limit properties. Now, if you recall, if you want to try to find the limit, there's a couple of ways that you typically start off with in calculus when you are just being introduced to this concept. One of them is, you would have a graph of the actual function. So if this, for instance, is our function right here, and we're trying to find the limit as x is approaching 0, we can graph it and then we can visually kind of see exactly what the limit might be. Now, our eye might deceive us, so that particular approach is not the greatest one to be able to have. It's going to give us approximations that we can carry out, and then possibly we can do some kind of guessing to find that out. Another way was just trying to see what the actual limit would be by going through the actual properties of the limit. So seeing from the left hand side, seeing from the right hand side, seeing if those limits exist, and then if they're equal to each other, then that limit exists, and then we can actually find out what that would be. And that process would be basically repeating, so this would have been limit, and this would have been as x is approaching 0, except this would have been, let's say, from the left hand side of this. And in order to do that, I would be able to substitute, for instance, because I'm approaching it from the left hand side, I would say, so x, I can substitute it and basically say 0. And then from the left hand side would be minus h, as h is approaching infinity. So it's approaching infinity, approaching 0. So it's basically getting smaller and smaller and smaller and smaller. And then we can substitute this into wherever we see x, and then we can see what happens. That would give us from the left hand side. If we wanted it from the right hand side, so if I would have put a plus there, then we would have substituted 1 plus h, because we're approaching from the right hand side, and then we're getting closer and closer to 0. Again, h is approaching 0. Now, this method is something that I've introduced. I'll put up a link up above there, and you can see that. But it's a lot of work, and it's not always nice to be able to manipulate, especially if we had something like this. It would have been annoying. So what we have noticed is that we do actually have certain limit properties which make it much easier, and we don't really have to utilize this method right here in order to find what the limits are. We can almost substitute the actual values in and then see what happens. So I'm going to present to you all the limit properties, that are kind of the most common ones. Now I'm going to make a couple of assumptions. So within here, I'm going to assume, so that we have two limits, of two different functions. So f at x, so that limit actually exists as x is approaching a. And then I'm going to assume that we have another function, so let's say g, of x, and that also exists as x is approaching a. If I know that these two exist, and them existing basically means that the left-hand side, right-hand side, they both exist and they're equal to each other, right? So that's what you see there in the table on the left. And then on the right-hand side, so what you see there, so this right here is the actual conditions for the limit to exist for g of x as x is approaching 2a. So I'm going to assume that those exist. Now I might say, okay, well, if you know that they exist, we can find it, but let's see how this actually moves forward. So here are kind of the simplest properties that we run into. So the first property occurs is when we're trying to find the limit of a function which is just a constant. So notice the function is c, right? So f of x is equal to c. And when this, function is just a constant, which really means if you graph it, it would be just a flat line, at c. There's nothing happening there, so it has a slope of 0, and it's just crossing your y-intercept at c. That's all that this would look like. Well, we know that this is equal to c, so the limit for x approaching any a, right, is just equal to c. And I'm assuming that x is defined, right? For basically, it's not being restricted in any way. It's basically the whole real line. So that isn't anything extraordinary, right? So it's just a constant. So the limit as x is approaching a, for any a, is always going to be equal to c, because it's just a flat line. Now, the other one is when we have a line which basically represents, so f of x is equal to x, which is a line through the origin, and it has a slope of 1, right? So it just crosses through there. We know, okay, that if we would try to find the limit, this just simply is equal to a. Now, surprisingly, these two things, again, they're not going to be anything extraordinary. Okay, so if it's f of x is equal to x, which is just a line with a slope of 1, well, as x is approaching a, so any a, it doesn't matter what that is, okay, of course, you might think that, oh, okay, yeah, that's right. I mean, if I substitute a into here, right, so it's always going to be defined, and basically what I'm going to find is it's just going to be approaching that a as I'm going through. With these two properties, we can now start to expand things out. And for instance, what we know by the properties is something like this, which is pretty neat. If you now have two functions, right, so f of x plus g of x, or for that matter, f of x minus g of x, okay, so this is just an addition or subtraction of two functions. Now, we know that the limit exists for f of x and g of x, okay, so that's our assumption from here. Then in this case, what is true is you can literally almost like distribute, okay, your limit across. Okay, so if you remember, if you had, so something, let's say if you had 2 and let's say you were distributing it across a bracket, this 2, well, you can do the same thing with these limits here. So you can distribute the limit across through, and you're going to get, okay, so here on the right hand side, that these two are equivalent. So to find the limit of the addition of two functions, it's just simply saying find the limit of one of the functions and then add it to the limit of the other function. So that's what happens. So instead of finding it for the whole thing, we can find it individually, add them up, and it's actually equal. That's a huge benefit for us. And the same thing is true for the subtraction. We can just distribute the limit across and then find out what that answer would be. Now, here are some examples of these. So where does this help us? So now we no longer have to graph this. If we utilize these properties, so notice within here, for instance, this is what's the limit as x is approaching to 2 of this function, which is a constant, which is just 5. Well, from the properties, we right away know that the answer is 5, right? So if we would graph this out, again, this is not a surprise because 5, it would have been somewhere over here. So it's just a line that is crossing through 5. And x, so maybe x is over here. So indeed, as it's approaching right here, it's just going to be approaching 5. So that's utilizing property number 1. Now, property number 2, okay, so this is this. Now I switched the x with a t. That doesn't matter. We're so used to using x everywhere, especially in calculus we use it. In functions we use it. But in real life, we use different variables as well. X is just a placeholder for some unknown quantity that we're probably trying to measure. So in here, this is really just property number 2. And property number 2 just simply means, okay, that the answer here is we can just substitute this into here and we're going to get 4 out without doing anything. So we don't actually have to show anything. We're just utilizing the properties. So that's super neat because now we can use, okay, those properties to find the limits without dealing with things like this, where we're finding left-hand side, right-hand side, okay, or graphing things out. So that's pretty neat. So those are 2 examples. Now, in terms of the distributing, so what we can do here is we can distribute this across these 2. So we can say that, oh, okay, so this is like my function fx minus and this right here is like my function gx, and that is like property here, I guess it would be number 4, okay, because I'm subtracting. So what I can do is I can just say this is the limit. I'm not going to write the x approaching -1. So limit, okay, 4 minus the limit, okay, of x. And notice that, well, this is a constant, so we know that this is 4. This right here is just x, so we know that this, as it's approaching -1, would just be -1. So if I'm going to be subtracting, okay, well, that means negative and negative will cancel. This would just simply be 5. So I can literally almost like substitute that -1 right in. And then 4 minus the -1 of the limits is just equal to 5. Now, for the addition, again, it's the same thing. So this is like saying this is my f at x. This is my g of x. Now, we know that those limits exist by property 1 and 2. I can now add them together. So I'm going to get the limit. This is as x is approaching 7, right? So this would be of x plus the limit of the constant. So here, this right here is just equal to 7. This right here is just equal to 3. And I add them together, I'll get that my overall limit is equal to 10. These properties are super useful to be able to utilize, without much of a fuss. Now, there are other properties which are also super useful here. We can continue and extend this. And you'll notice a pattern that, these examples I'm giving you, basically, it's functions that are constant, functions that are linear, right? So just basically lines that I have. But we're going to start expanding it into polynomials. We can expand it into rational, okay? And even we can have radical functions. So you'll see that we can do that. And of course, you're going to be able to expand it to others as you're going along in terms of, sines and cosines, so all the trig ones in the future. But let's keep it a little bit simpler as we're introducing this. So here are the next set of properties. So here are 3 properties that I would want to be able to outline for you. Now, here, again, it may not surprise you. So notice if I have a function, so right here, and I know that this limit exists. Now, multiplying this function by some constant. So I have some constant c, so maybe some number. I don't know, 2, 5, so some particular number, which is fixed. Then it turns out that you can bring that constant, so this constant right here, you can bring it outside and bring the limit right inside of this. And since we know what the limit of this is, then we can just multiply it by c and we get our answer. So that's fantastic. And I'll show you an example of how that can be applied. The one just below it, the property there, so if you're taking a limit of now 2 functions being multiplied, so notice if I'm multiplying, if you know that these 2 limits exist, then again, it's almost like you can distribute within the actual multiplication. So notice what I did was right here, I can say, well, this is just equivalent to taking the limit of the first function and multiplying it by the limit, okay, of that second function that I have there. So that's, again, super useful because if we are going to have 2 functions multiplied together where we know that the limits of each exist, we do not have to distribute or multiply these functions before we start taking the limit. We can just take the limit of each, multiply the limits together, and we're done. Now, if multiplication works, then you shouldn't be surprised that division, okay, or the quotient there will work as well. So multiplication in terms of the product, okay, quotient in terms of division, it's the same thing. And in reality, division is really multiplication by kind of the reciprocal of a function. Now, we do have to be careful here a little bit because this is the same thing as worrying about rational functions and where they're defined. So if these limits exist, right, then we can certainly divide them. Now, the only 2 things we do have to note is, what happens if we have, so if this is, maybe the numerator, I called it n in here, so n is not equal to 0. But what if the denominator was equal to 0? So we basically run in that we would have had an undefined result. Undefined results simply mean that the limit cannot exist. And that, again, should not surprise you because it will mean that the functions may not be defined there at all. Okay, so that's 1. And you're dividing a number by a 0, okay, which is simply undefined. And then there's no solution to that. So there would be no limit either. The one tricky item is, and this one, if you do have something like this that happens. Now, if you don't have a 0 in the denominator, then you're good to go. You're actually going to get what the limit is. But if you do have a 0 in the denominator, you have to be careful. So one thing is, if you get undefined result, no limit exists. If you get indeterminate result, which is 0 over 0, in this case, okay, the limit may exist. So in that case, it's basically sometimes referred to, you may see it as a removable discontinuity. And I'll talk about that. Actually, I'll mention that in another video. I'll show you one example here. But if you want to see, limits and discontinuity, I'll put up a link up above there. Once the video is up there, okay, you can take a peek. But it won't be a discussion here in terms of limits and discontinuity. What I did want to mention is that this should cross your mind. What happens when you're dividing by 0? And again, if it's undefined, no limit. But if you get 0 over 0, then the limit may exist. And you do have to be careful. Because 0 over 0 just simply means it's indeterminate from the result itself. So you might have to do a little bit of work there in order to find out. Okay? And I'll show you that. So here are some examples, right? So now, okay, so we have something like this. So what we can do is, okay, so again, I'll skip writing this, okay, because I hope that you can see that. We would have to write it here to be, correct. So if you're writing it for your teachers, please still do write it, or just ask them, do you have to keep writing that? Because it just takes a little bit of time. But here the limit, because always below the limit we say, like, what are we approaching? So what this means is, because this is a constant, I can bring it out, and then I can just take the limit as x is approaching to -2 of x. But hey, wait a minute, that was my second property, right? So this was nothing else but simply 8, and then, so this entire thing right here is just equal to -2. And now if I multiply, I'll get -16, and I would have gotten the limit, right? And I'm using this property right here. So that's pretty neat. The second property, so within here, so I have a few things happening. Notice there's a subtraction, so that's 1. So I would have said, okay, so this would have been limit. This is my like my fx, this is like my gx, all right? And now I would have had 3x minus, and then the limit of 2. Now again, so I noticed that here this is a constant, so I can bring this out. So this is going to be 3 times the limit of x minus, now this is the limit of a constant, so this would just be 2. Now I substitute for 1, so 1 into right here, so that is just 1. So 3 times 1 is 3 minus the 2, okay? We know that the result would have been 1. And you might start noticing that, it's interesting. It's almost like I'm just plugging it in. And it is true, when the functions are very well behaved, they're continuous and so on, that's exactly what happens. But I do suspect that if you're kind of probably in the first chapter in calculus and your teachers may ask you to show this work, right? That you understand the properties and why you can actually substitute in, okay, because you're distributing the limit across the different functions. So that was another example. Here is, something like we almost started with. And now notice this is going to be so much better to do. So for this one, maybe I'll copy this down and I'll bring it down. I'll come back to all of these just a moment. So let's maybe do that so it doesn't bug you there. So this we can distribute. So I can say the limit. So this would have been like my fx. This is like my gx, so it's like I'm multiplying two functions. So now this would have been the limit. I'm approaching 0, so this would have been of 0.5x plus 1 multiplied by, okay, the limit, and this would have been of 3x plus 2. So that is the property with the multiplication. Now, again, if you had to show this to your teacher, okay, so this again, so now you have two things. So this would have been limit of 0.5x plus the limit of 1. So that's from right here. Okay, so that's that. Multiplied by the limit of 3x plus limit of 2. So you're breaking it down into smaller and smaller pieces. And now within here, this would have been the 0.5, that's the constant. So limit just of x plus limit of 1. This is as x is approaching 0. So this would have been basically 0 plus 1. So that's right here. And then here I would have gotten, so within here, on the right, I would have said 3 limit of x plus limit of 2. This right here, so again, would have been 0 because this, okay, tends to 0. And then this would have been just simply 2. So this whole thing would have been 1 multiplied by 2, so the limit is just 2. And again, you might say, well, why didn't I just substitute it all into here, meaning x equals to 0, and then I would have gotten the same thing. Yes, it's true. After a while, that's what you're going to do. But if you had to show to your teachers, you would actually have to do this, right? So you'd have to go through this junk because this actually shows that you understand the properties that you are utilizing. So that would have been the example of this one. So let me remove this out. So delete. All right. And now you have some other examples here. So that was this one. So we said this was 2. And now you have some kind of divisions, okay, or quotients there. So now let's take a look how we would do this. So again, this is like, you know, you have f of x on top, and here it's like you have g of x at the bottom, right? We want to be able to see. Now notice that we're not going to run into the problem of the denominator being 0 in this case because we're approaching 2. So everything is going to be fine. So this is just simply like saying limit of negative x all over limit of 4 minus x. Okay, so that would have been the first step. Second step is that negative can be taken out. So limit x. And then here, unfortunately, I would have to go limit of 4 minus limit of x. So I'm just distributing across there in the denominator. Now, this whole thing, so as x is approaching 2, so now I can comfortably say that's negative 2 all over. And then this would have been 4 minus the 2. So this is negative 2 over 2, which is simply negative 1. And that's what we would have gotten for that. And that's the work, okay, that we would have to put in. So that's another example there. So negative 1, that's what we would have gotten here. Now, here on the next one, we do run into a problem. Notice that the denominator, so x minus 1, so this function is actually not defined at 1. Right? Because it would be 0. And indeed, we would run into a problem because we would get limit of 5x plus 2. So we want to find that all over limit of x minus 1. Now, if I do the numerator, I'm going to get limit of 5x plus limit of 2. And then all over limit of x minus limit of 1. So far so good. Now this, okay, right, this 5 I can bring outside. So I'm going to get limit of, so 5 times the limit of x as it approaches 1. So that's just simply 5. Plus, this is going to be just a constant, so 2. And then at the denominator, I run into a problem because I'm going to get 1 minus 1. And notice it's going to be 7 over 0. And that's undefined. And that would tell us when it's undefined, no limit exists. And that shouldn't surprise you, because if you would plot this out, you would get an asymptote, okay, at x is equal to 1. So that would have caused us another discontinuity. Okay, and again, if you're interested in that, you can watch that link that I pointed out on discontinuities. So that's another example that you would get. And now here, the last one, okay, so for this is actually a good one. So let me remove this right here. I'm going to switch the color. Now, for this one, notice what we would get. We would get limit x, and then this would have been x plus 2 all over. So if I'm just blindly trying to do this, I would get that as I'm using the properties. Now I would get limit of x multiplied by limit of x plus 2. Now I do have a problem because limit of this as x is approaching 0. So now I know that I'm going to get 0 on the denominator. But I also will see that, but limit of x here also is 0, right? This limit, as it gets spread through here, okay, that would have been just 2. So what I get is this, which is really 0 over 0. And that's indeterminate. And in this case, you cannot say that the limit does not exist. In fact, the limit does exist. And the limit is equal to 2. Now, why is this the case? If the properties lead us to this, and that tells us that it's indeterminate, we can't stop there. We have to use a different method. Now, please remember something, that when we are doing limits, we're approaching 0, but we are actually never at 0. That's why when people say, I'm just going to substitute, right, 0 into the whole thing, that works as long as the properties all hold through. But the technicality is that it's never at 0 in this case. Remember, now you got to go back to the original, which means from the left-hand side I'm approaching, and from the right-hand side I am approaching. And if you remember from functions, this is actually, you would have had a hole. And this is nothing else but simply a line. Now, why would you have a hole at x is equal to 0? Because notice that x and x, right, would cancel, and you would simply get x plus 2 on top. And for x is approaching 0, so that means it's some number, but it's getting closer and closer to 0. We can do that. We can actually do this. This is actually called the removable discontinuity here. And within here, now all I have is now I'm only dealing with this. And if I'm dealing with this and I'm trying to find the limit as x is approaching 0, well, that's not bad because this would be just 0 plus 2, which is simply 2, as I said. And I hope that you can see now, the point is that as you're using the properties for the quotient, for the division, be aware of this. Do not just stop here. And, let your teachers know, okay, this is indeterminate. Now I have to go back. And now the teacher will see, do you really understand the limits? All right. So that's what would actually happen. Okay. So within here, and what this function looks like, if you graph this out, you can use decimals if you like. This is just a function that basically goes through, okay, so it's going to go through, okay, 2 right here, but it's going to have a hole. It's not defined there, and then it continues on. So it's going to look something like this. It's a line, and then it has this, and that's why we call it removable discontinuity. It's discontinuous because it's not defined at that particular point, but it's defined everything else. And notice, as x is approaching, right, so as it's going in this direction, okay, and going closer and closer to 0, it is approaching 2, right? That's the limit. All right, so that's what you would have had here. Now, there are some other final properties that I have for you here, and some final examples as well, which are pretty cool. So the next one is, notice that on all of these examples, we had no exponents, right? So now what happens if you do have an exponent? So you wouldn't be probably surprised that what that means is you can bring in, okay, and take the exponent outside and simply take the limit of the function and then raise it to the exponent. Now we are assuming that our exponent is a rational number. So rational number, okay? If you've maybe forgotten rational numbers or like natural numbers, whole numbers, and so on, I did a short introductory, even a playlist. This goes back way back into kind of elementary school. Put up a link up above there. But rational numbers you can think of as basically integer on top, integer at the bottom. Okay, it's like a fraction. So these exponents, okay, this is pretty useful property to have. And now the other component is, this is almost an overkill in terms of a property, but sometimes, you know, you'll see it in textbooks or teachers will show this to you. It's the root, okay? Now the nth root, so that could be square root. So that would mean, if you say square, that means n is equal to 2. We just don't write it. But it can be the third root, fourth root, fifth root, and so on. So when you're dealing with radicals and you're trying to do this, remember that radicals are basically just exponents that are fractional exponents. Again, I'll put up a link up above there where you have radicals and fractional exponents. I did a video on that. I think it was related towards grade 9. Okay, if you forgot. Doesn't matter. Okay, for radicals, what we can do is we can bring our limit inside the radical and find what the limit is of that function, and then take, okay, the actual, you know, root. Okay, so the nth root of it. Now, we do have to make sure that that root actually exists, because remember that it doesn't always exist. So, you know, if you wanted to take the square root of -2, well, this doesn't exist. We cannot take that. Now, but if it was the third root of a negative, that does exist. So that again brings you back to understanding your roots and then your exponents as well. So here are some examples, okay, within here. So how would this look like? How would you break it down? Okay, so now I would break it down like this. I would say limit, this would have been 4x squared plus limit 2. So I'm bringing that in there. Now what I have in here is, this is a constant, so this would have been limit 4 limit of x squared plus, this actually I already know what that is. That's a constant, so that's 2. And now because I have an actual exponent, so what I can do is, this is the same thing as saying 4 times the limit of x and then square that limit plus the 2. That's how you would show your teachers. And then now this is just 4 limit x, we're approaching 1. So that's just simply 1 squared. 1 squared is 1. This would be 2. And then this becomes 4 plus 2, which is equal to 6. So you have to do all that work to show. And then, of course, in this case, we do not run into any problems because of the fact that 4x squared plus 2 polynomials are super well defined. So, you know, we can literally substitute and we'll get that 6. But this is how you would show your teachers if you understand your properties or not. So that's one example here, okay, that I have. Now, another example. So this is just bombardment of examples for you. So what about this one? Well, this one I would say this is limit. This would have been x squared. So this is all over. And now this is now limit of 4 minus x. That's step 1. Now I would say this is limit of x. Again, I can take the square out all over. And this would have been limit of 4 minus limit of x. Now we're approaching -3. So this would have been -3 squared, right? So that's what you would have gotten there. So that would have been 9 all over. And then this is just 4 minus, so this is 4 minus -3. So we're approaching that. So that's 9 all over. That would be, I guess, 7. And that's our limit. There we have it. So we broke it down for the teacher, okay, in terms of all the different properties that we're using. So Sometimes even the teachers might ask you, what property you are using. So, if it's addition, subtraction, if it's the exponent one, if it's the product one, so multiplication of 2, if it's a quotient one. So, just be careful with those, and then, let your teachers know. These last two examples are actually really good, and they do highlight something which you should think about before starting to apply all the different limits that you are actually interested in finding. So let's tackle these. Now, with radicals, we have to be careful. Now, we have to be careful with all functions. And one of the things that we have to be careful about, which we didn't really do in all the other examples because they were very nicely defined, is we should, before we start going into the limit and utilizing the properties, we should actually take a look where the function is defined. Okay, so here's, for example, the highlighted one. Now these are the same ones, right, that I'm going to have, and you'll notice that for both of them the limits actually do not exist. Now, if I just blindly applied the limit properties without checking where they are defined or not, this is what I would find. So I would say, okay, well, I can apply the properties, so I can bring in the limit. So I would say limit of negative 3x, and then this would be all over the limit x plus 0.5, and then I could put the radical over. Then I can proceed again. So inside the radical, so negative 3, limit x all over limit of x plus limit of just the constant 0.5. And then I would say, oh, well, this, okay, as it approaches 0 is 0. So that's negative 3 times 0 would be 0 all over. This would be 0. And then this would be 0.5, and then I would find, well, this is 0 over 0.5, which is just 0, okay, and there you go. Now, here is the problem, okay, so what happens, so please remember that when we say x tends towards 0, when we say this statement, what it means is that when we are looking at the x, okay, axes, so in this case, we're actually trying to approach from the left and the right, in order to do that. We need the left-hand limit and then the right-hand limit to exist and to be equal. Now, we do not have a problem if there is no radical with this. It could have worked out perfectly fine, right? And then we would get our answer for this, right? So if we have a radical, then we have a problem, because notice that on the right-hand side, okay, of the x, so as x is positive, this actual radical does not exist. And the way that we see that is, so notice if we say negative 3, all right, x all over, this is x plus 0.5. So as we make, as we're on the right-hand side, as small as we want it to be, notice what's going to happen. Okay, so if x is positive here, then we're going to get negative 3 times a positive number, which is going to be a negative number, correct? So negative times a positive. That's on the numerator. Now, in the denominator, so this won't really make a difference. So x is positive, so this is a positive plus another positive. All right, so this is a positive. So what we have is we have a negative number, but we're trying to take the radical. We're trying to take the square root of that, but the square root of a negative number doesn't actually exist. So the limit as x tending towards, okay, this is from the right-hand side, actually does not exist for this. But yet, if we blindly applied these, then, we would have run into trouble, because we would have said, oh, this is equal to 0. Now, how could we avoid that? Well, in order to avoid it, you actually have to take the original and actually find where it is defined beforehand. Now, this wasn't really necessary for us to do in the past, but you should kind of have that first step in. So first find where is it defined. All right, so where is this defined? And only then, can you actually talk about the limit itself and then utilizing the properties. So for this, what we know is that this is actually defined. However, x has to be less than or equal to 0. So it can't be positive, because if we have it positive, then this radical doesn't exist. So that's one. Now, the other problem that we have is, notice that in the denominator, okay, well, x is definitely not going to be able to be negative 0.5. So definitely x cannot be equal to negative 0.5, because if it is, then we will have our denominator equals 0. So it's not defined there. Now, just because it's not defined there doesn't mean always, as we saw, that there is no limit. However, okay, we're trying to see where it is defined. Now, what about, so as we're going along here with x, so what we found, okay, so this is x, so we know that we're kind of stuck at 0, so it's not defined over here. And now we have a problem here at negative 0.5 as well, right? So it's definitely not equal to that. And now what about to the left of it? Right? Okay, so what happens here and then what happens here? Is it defined in these two regions? And in order to do that and find it, so over here, so you can certainly substitute something which is bigger. Now, it doesn't really matter what it is. I can substitute -1, for instance. So you would have -3, times something which is bigger. So obviously this is going to give us a positive in the numerator. But in the denominator, if we make it less than negative 0.5, whatever that might be, then notice that this, if this is less, then this whole thing is going to be negative. So once again, we find that this is negative, and we're trying to take the square root of that. So that means it does not exist over here as well, which, okay, right off the bat, if I scroll up here, if we're trying to find the limit as x is approaching -1, this thing's not even defined at -1, right, at all. So, so we know that this limit does not exist, that's for sure. And now we also know that this limit does not exist as well, because we can't take the limit from the right-hand side, as we saw over here. Now, it may, this function is actually defined in that region. So the actual domain for this, so my domain would be that x is equal or less than 0, but it is greater than -0.5. That's what we would have here. And let me just graph it for you so that you can also see it. So you have to be careful with this, and I do encourage you to try to understand, where is a function defined. And this kind of goes back to, advanced functions course that you would have. And I can put up a link up above there, to seeing, how do you find these kind of, where is a function actually defined. I'll try to put a link to the video, or you can take a look at my playlist for the advanced functions, and you'll find that there. So in any case, let me load Desmos. Here is Desmos, and I'm going to just put this in here. So square root -3x all over x plus 0.5, and notice what happens. So this is how the function looks like, and indeed it looks like it's blowing up on us, right? So it's never really touches -0.5, right? Like it just starts blowing up as we get closer and closer, which makes sense because it's in the denominator, so make it bigger. And then notice as we're approaching, so basically as we get to here, we can get to 0. We get 0, 0. But we can't have a limit at 0 because of the fact that we can't come in from the right-hand side of 0. So the only limit that would exist would be from the left-hand side. So for instance, if they gave us, so right here, if they, said, what's the limit from the left? Well, the limit from the left is 0. Then indeed you can apply this and this will work from the left-hand side. But the limit from the right-hand side does not exist because we can't come in. The function is not even defined on the right-hand side. And therefore the entire limit does not exist. So I think this is, it's a very hard example, but it's worthwhile for you as a student, if you're watching this, to really comprehend this. All the properties are wonderful. We didn't run into these problems, so really you just saw it here with the radical, right? But you do have to watch out for that when you are applying those properties. Don't just apply them kind of blindly going in. It works very well for regular polynomials, right? No problem. For, if there is a rational function, just be careful about the denominators. Okay, so that's something that you have to think about. As you stem into and you get into radicals, you do have to watch out over here and see where these functions are defined, where they're not. Because the teachers might kind of try to trick. I mean, it's mean, but it really forces you to think about limits. And do you understand that original definition of limits, okay, which was this. Left-hand side, right-hand side, and they have to be equal. All right, thanks for watching. Okay, we'll see you in a future video. Sorry for the very long one here. Bye, everybody.